Hello, everybody, and here we go into our next chapter, chapter 17 for TRO, and it's going to be, generally speaking, an intro to acids and bases. It's going to lay a foundation for a whole lot of work that we're going to do in later classes with reactivity, and a lot of the discussion about the rationale for acids and bases will carry forward when we talk about nucleophiles and electrophiles, and just really, really important conceptual material. So, to kick it right off, acids and bases. So general properties, we're going to start a really broad, low level, and then start zooming in progressively. And thankfully, unlike so many things in chemistry, we have a intuition for discussions around acids and bases because it's things that we encounter in our daily lives and it's part of our vernacular. So common properties of acids. Not that you're going around tasting acids in the chemistry lab, but we do it all the time dietarily. So acids typically have sour flavors. Additionally, they're really useful for dissolving numerous metals. There's exceptions to that, but a lot of metals are dissolved by acid. They have the generic property of neutralizing base. And if you're, in lab and you're using litmus paper to assess a pH, they will change a classic litmus paper from blue to red. Oh, might as well look at this here. And here we have an example of acetic acid, which is the primary acidic component of vinegar. Make sure when you say the word acetic acid, you enunciate so that it does not sound like acidic acid, because all acids are inherently acidic, yet acetic acid is also acidic, yet is its own distinct thing. So this is, we'll see, will be a weak acid due to this carboxylic acid group, with this proton here being our acidic proton. So other common acids that we might be interested in, you should be comfortable with most of these in terms of their name and what their chemical structure is so that you can recognize them rapidly as an acid. Just right off the gate, we have hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, acetic acid, citric acid, carbonic acid, hydrofluoric acid, etc. Now note that these are drawn a little bit differently. That's because when there is an organic structure which has an acid, we pull the hydrogen out to the front to show that it's an acidic proton. So in this case, HCl, the hydrogen goes up front instead of near the end, and that identifies it as an acidic compound. Also, for sulfuric acid, we have H2SO4. That's because both of those protons are acidic, although one, as we'll find out near the end of this chapter, is more acidic than the other. Same for nitric acid. Acidic proton pulled to the front. And acetic acid, citric acid, etc. all have their acidic hydrogens pulled to the front. And as I mentioned before, I will refer to these acidic hydrogens as protons quite commonly because, as we remember, a hydrogen has a molecular weight of 1 because it does not have a neutron. Its nucleus only has a proton, and it has a single electron. So if you lose a if you lose a hydrogen, let's say it's bound to something, it's usually because something pulls that hydrogen off. But if you lose this, let's say, in this fashion, I don't want to overcomplicate it. If you lose a hydrogen and it's floating around as H+, what that literally is a proton minus its electron. Therefore, this H+ is literally a proton. So I use those interchangeably quite a bit throughout this. And we'll discuss it a little bit more down the road, but I'm hoping to avoid any confusion regarding that usage. So, structures of acids. Our basic binary acid would include our acidic hydrogen or proton attached to a non-metal atom. So good examples of this would be hydrochloric acid, hydrofluoric acid. Now, to get a little bit ahead, what makes this acidic? Well, Acids, well, we're going to get into, are good at giving up protons, and we have different ways of viewing what makes them an acid. However, remember from 105, chlorine is electrophilic, so it's good at housing electrons, whereas hydrogen is not electrophilic. It's okay losing electrons, and this goes back to our discussion around establishing noble gas electronic structure. So in a situation where you have hydrogen bound to chlorine, it's not that hard for the electrons that are being shared between the hydrogen and chlorine to go completely to the chlorine. And this makes for a free proton, or acidic proton, and a chloride, both of which have noble gas electronic structure. So, with the exception of this, because it doesn't really have electronic structure because it doesn't have any electrons. So this is what makes it acidic, is the ability to give up a proton. There's a chemical rationale for why it's able to give up its proton. Likewise, we have other structures to acids, which include our oxyacids, in where the acidic hydrogen is attached to an oxygen atom. So good examples of this would include our sulfuric acid and our nitric acids. And both of these are also good examples where we have electronic structure which supports the loss of this hydrogen, which makes it acidic, where we can have polyprotic ion of NO3- quite easily, because we can house that charge on this oxygen, which is then distributed via resonance equally over all three oxygens. This allows us to distribute that negative charge over three positions, makes it relatively stable, and also gives us a nice double gas structure, or octet rule structures. So that supports the formation of this free proton, or acidic hydrogen. Other structures that you'll see quite a bit that are acidic include our carboxylic acid structure, which we list as COOH all the time, but it's actually drawn three-dimensionally like this, where you have a carbon that's bound to two oxygens, one of which has a double bond, and the one that has a single bond has a hydrogen on it. And this hydrogen can readily fall off, putting the electrons onto that oxygen, which are then distributed via resonance between the two oxygens. So a couple properties of bases. Bases typically taste bitter, and alkaloids are examples of good bases that are produced in the plant kingdom. And often, these alkaloids can also be poisonous as well. And any of you who've handled, say, bleach before, notice how slippery it is, right? When it's on your hands and you're washing your hands and they're slippery as you're getting the bleach off of you. That's because bases are often slippery. If you're talking about red litmus paper, they'll turn blue, and they have the generic ability to neutralize acids as part of their neutralization reaction. A couple common bases we should be comfortable with. Sodium hydroxide, potassium hydroxide are great strong bases. The hydroxide component, or OH, is what makes them basic. And then the sodium and potassium are your counterions, your countercations. And then some weaker bases include sodium carbonate, sodium bicarbonate, and ammonia. And these are things that are going to pop up regularly as part of word questions. So just be confident in what sodium and potassium hydroxides, bicarbonate, carbonates, and ammonia are, and that these are all common bases and have basic properties. So there's really two initial definitions of acids and bases we're going to work with, and then at the end we're going to add a third one, the Lewis definition. But right out the gate, let's focus on the Arrhenius definition and the Bronsted-Lowry definition. So the Arrhenius definition, our first bullet point here, which describes an acid, is that an acid produces protons in solution, and that bases produce hydroxide in solution. So acids produce protons, bases produce hydroxide. And this book is technically correct in that protons always associate with water to form hydronium, which is H3O+. So whereas water has a Lewis dot structure that looks like this and is neutral. Hydronium has 3 hydrogens because one of them has been added as an acidic proton. And because it's just so reactive, and it's reactive with the water, that it's always going to form hydronium in an aqueous solution rapidly. Now, that doesn't mean that I'm going to nitpick you guys over the use of hydronium versus free proton when you're balancing acid bases in terms of correctness. I'm super happy with either as long as everything's technically correct. That's just my caveat to this. But when you're looking through this book, they're going to refer strongly towards hydronium being your free expression of acid in an aqueous solution. But occasionally they'll also go interchangeably back and forth between protons and hydroniums being your forms of acid. Now, the Bronsted-Lowry definition doesn't lean on base-producing hydroxide. Instead, it refers to the differentiates between the two as one being a proton donor, which would be your acid donating proton, and one being a proton acceptor in the case of the base. Because not all bases have hydroxides. So let's start with the Arrhenius definition here and go into a little bit more detail. So under the Arrhenius definition, substances that produce protons or hydrogen ions, cations in aqueous solution are your Arrhenius acids. And so a good example of this would be this strong acid, hydrochloric acid in aqueous solution separates into its counterions. You have your proton in aqueous solution and you have your chloride in aqueous solution as your cation and anion respectively. So this meets the definition of producing hydrogen ions in solution. And here we go, the hydronium ion. Technically, proton don't exist in water in free form because they're so reactive. So what they do is they react with water to rapidly form hydronium ion or hydronium cation. And this is technically correct. Now, the thing is that this is not a super stable compound. The hydronium behaves as acid because it has that extra proton, and it's super happy to give it back up and become water because water is more stable than hydronium. Big surprise there, right? So it's totally content to just become water again and give up that proton to something else as part of an acidic reaction. And we're going to get into some of those things later. But I don't want you guys to think when you see hydronium that that's a stable outcome. When you see hydronium, I kind of want you guys to think acid. Okay, Arrhenius definition of bases are that substances that produce hydroxide ions in aqueous solutions are bases. So in this particular case, example, we have a strong base, sodium hydroxide, and when put into water, it's going to separate into its sodium cation and hydroxide, which should have a negative charge associated with it, anion. And that production of hydroxide is what defines it as an Arrhenius base. So, reactions. The general reaction that we always see with any acid-basic combination is a neutralization reaction where the hydrogen cation combines with the hydroxide anion, producing a molecule of water, and this is what we're talking about with neutralization, is an acid reacting with a base to produce water. And we will see that general form all the time, and when this happens, the counterions then recombine to form a salt. Now that salt may be aqueous, or it may be, a precipitate. Regardless, in this example, it's an aqueous salt, sodium chloride, meaning the sodium and chlorine are not bound to one another in an ionic matrix. They're floating around as cations which are dissolved in the water. But regardless, you can see we have our acidic proton in our hydrochloric acid, and we have our basic hydroxide in our sodium hydroxide, and those two things are going to react with one another to form liquid water as part of our neutralization reaction. Now moving on from the Arrhenius acid-base theory, let's look at the Bronsted-Lowry theory a little bit. This one's a little bit more widely applicable because it doesn't rely on the production of a hydroxide to define a base. It just needs something that can accept a proton as part of an acid-base reaction. So, conveniently, all reactions that fit Arrhenius definition also neatly fit into Bronsted-Lowry definition, but Bronsted-Lowry definition gives us a little bit more flexibility in defining other bases. So, under this definition, once again, the acid donates the proton, very similar to what we were just discussing previously. However, in this case, the base is a proton acceptor. So we typically show base structures which contain an unshared pair of electrons, which are willing to donate those electrons towards binding a free proton. And this is very amenable to that proton because the proton wants to have those electrons, because remember, it is lacking in them, which is why it has that cationic charge. So the general reaction is listed below here. And let me just to clarify something. This is not really drawn with bonds as long as they ought to be. That little dash is supposed to be a full-length line. Excuse me. So here we have this acidic hydrogen H bound to molecule A, which is part of the acid, and then we have this base B, which has a lone pair of electrons which it's happy to donate. And this is almost always a reversible reaction if it's a weak acid base. And what's going to happen in this case are these electrons on the base are going to swoop in here and grab that proton. And it's going to push the electrons from the existing proton acid bond to the acid. And what this is going to do is it's going to put extra charge on our acid molecule minus the proton, putting the lone pair on the acid and giving it a negative charge if it was neutral before, like in this example. And now we've made a new compound. But now this compound has a positive charge because it was neutral before, and it no longer has that lone pair because those electrons are now busy binding our proton. So this is just rationale. I'm never going to ask you to push electrons like this in this class, but it's always nice to kind of see what's going on, I think. So even though I'm not going to quiz you on it or test you on it, I always appreciate a little extra rationale when I'm in this kind of class. So, Bronsted-Lowry acids. Once again, remember, Bronsted-Lowry are proton donors if they're acids. So, any material that has a proton can potentially be a Bronsted-Lowry acid. And that's actually going to become something that we're going to talk about in depth over this chapter and the next chapter, is that acidity and basicity are really relative terms, because something that's relatively acidic can become basic if it's put in an environment which is vastly more acidic. It's all relative. So, and there's limits to that for this class because we're dealing with all aqueous solutions and fairly common things, so we'll keep it fairly simple. Regardless, keep in mind that acidity and basicity are relative. So when we say any material with a proton can potentially be Bronsted-Lowry acid, yes, that's true, but is it a good acid? Not necessarily. So don't try to keep those two concepts separate. So let's see here. Basically, using this definition here in this example, we have hydrochloric acid as our acidic compound. When it's dissolved in water, hydrochloric acid, we'll see, will fully dissociate, and this will make all of its protons available as acidic protons. And in this case, water is going to be our base because water is able to rapidly react with those protons forming hydronium that we've seen. So in this case, our acid in this case is hydrochloric acid. Our base is water. And hydrochloric acts as the acid because it donates the proton. You can see it giving it up. And the base acts as the base, Bronsted-Lowry definition base, because it accepts the proton. So, the opposite of this is, what's a Bronsted-Lowry base? It's a base that, a compound which accepts protons. So technically, any material which has atoms within the molecule which have a lone pair could potentially be Bronsted-Lowry bases. Now, it doesn't mean it will be an exceptional one or even a very good one, but has the potential to be one. So we always have to look at if an atom is more willing to accept that proton than another to define whether or not it's a good Bronsted-Lowry base or a poor Bronsted-Lowry base, despite it having the potential to be a base. So in this example, let's look at one of our classic bases, ammonia. It's a weak base. It has a nice little lone pair of electrons. If we looked at its Lewis dot structure on the nitrogen, and because of this, it can actually abstract a proton from the water, and that will form hydroxide actively. So in this particular case, the base is accepting a proton, and the water is donating the proton. So in this case, the ammonia is our base, and the water is our acid. Now you might think, that's interesting, because the prior example, water acted as our base, and you would be correct. That's because water is an amphoteric substance. So an amphoteric substance is any substance which can act as either an acid or a base, because they have both transferable protons and they have an atom which has a lone pair on it. So in the case of water, it meets our criteria. We have two transferable protons and we have two lone pairs. So it's a pretty exceptional amphoteric substance. So it's very easy for water to act as a base, like we saw in our previous example, where we have a strong acid react with water, forming hydronium. You can also have it act as an acid, where it reacts with a base, in this case ammonia, forming hydroxide. Now, one of the advantages of using the Bronsted-Lowry theory is that it really illustrates the reversible nature of these reactions. And as we drew before, remember, let me see if I can draw this in a little bit better. This little short bond is actually a long bond, and this is the full-length bond. There we go. Now we have some nice bonds drawn in. In this particular example, generic acid reacts with a base, and the acid is deprotonated, forming our new compound, and the base grabs that proton. And you might think now, oh, well, this is interesting. This is really interesting. But when this happens, remember that now we have this lone pair over here. And now we have, right? So if this now meets the definition of a base. And our base, or what was our base, now has an exchangeable proton attached to it, and it looks like it might behave as an acid. And this is the rationale for these reactions being reversible, completely reversible. So this takes us to the next concept of conjugate acid-base pairs. Because by deprotonating an acid, you make a conjugate base. By protonating a base, you've made a conjugate acid. And let's dive down that rabbit hole a little bit. So, we always talk about these reactions in terms of conjugates, pairs of acids and bases based on whether or not they have that proton attached to them. So in the case of ammonia here, which is our base, we have this nice little lone pair of electrons hanging out above the 3 protons. If you add that proton, that 4th proton, you get ammonium cation. Now that this base has the new proton attached to it, it is now the conjugate acid to that base. It now has that extra proton, and this proton can leave and behave as an acidic proton in other reactions depending on the conditions. Likewise, we have water, in this case behaving as an acid, and you can remove that proton, react it with something else, say ammonia, and this is going to produce hydroxide as its conjugate base. Now the water's core identity shifts from being acidic to basic. So whenever you have a balanced acid-base reaction, like we have right here, where you have ammonia reacting with water, forming an equilibrium solution of ammonium and hydroxide, you can see that the base accepts a proton, becoming a conjugate acid, and the acid donates that proton to the base, becoming the conjugate base. Conversely, that's going this direction, forward. If we look at it as reversed, the hydroxide acts as a base, grabbing this proton, fourth proton, from the ammonium, and becomes the conjugate acid, water, right? So this is, like in the last chapter, dependent on the direction by which you're viewing the reaction. So let's do a little quick conceptual connection. Which pair of these compounds is not a conjugate acid-base pair? And this is all about the presence or loss of acidic hydrogens. So in this particular case, we have a compound which has a nitrogen attached to 3 methyl groups. It has a lone pair attached to it. This, conversely, has an acidic proton which reacted with that lone pair and added a positive charge because we were neutral before bringing the proton to the party. So that looks like a conjugate base pair to me. B, we have H2SO4 and H2SO3. There's nothing acid-base about this. The number of protons did not change, the charge did not change. What changes the number of oxygens, and that has nothing to do with our acid-base chemistry. So right out the gate, without assessing C, we know that B is not a conjugate acid-base pair. And looking at C, we have HNO2 and NO2 minus. In this particular case, this is our acidic proton as drawn with the hydrogen up front. If you were to lose that hydrogen, you would get a conjugate base NO2 minus. So that makes sense. That is an acid base conjugate pair. And that is the correct answer, B. So I keep talking about good acids and good bases. And that really parlays into this discussion of acidic strength. How strong is the acid? How strong is a base? Well, let's start with strong acids in general. Strong acids are strong electrolytes, meaning they fully dissociate in aqueous solution, meaning they, well, practically completely fully dissociate. Fully is a very strong word, but for all intents and practical purposes, fully dissociate, meaning if you have a strong acid like, say, hydrochloric acid, when you put this into water, spontaneously, we will get nearly 100% protons and chlorides in charged form, and those are both reacting with water, with that proton reacting with water forming hydronium, and the chloride being surrounded by the partial positive charges of the water molecules, kind of forming three-dimensional partial charge interactions. For the exact same rationale, strong bases are also strong electrolytes. So if we were to look at sodium hydroxide or potassium hydroxide, we're going to get nearly full dissociation of the sodium and potassium, liberating free hydroxides into solution. Now, conversely, weak acids are not strong electrolytes. They're technically weak electrolytes, meaning that only a small percentage or a fraction of the molecules will dissociate. So only a part of the hydrogens that are acidic will leave. So you'll only be forming partially of a mixture of your conjugate acid-base pairs, and some will be unreacted. Meaning, anytime you have a weak acid, you're going to be looking at an equilibrium solution. Same rationale for weak bases being weak electrolytes. Because they're weak electrolytes, you will not get that full dissociation you're only going to have an equilibrium in which some of the base is behaving as a base at any particular moment. So let's look at the strong acids first because they're a little bit easier to discuss. So once again, they donate practically all of their protons to the aqueous solution right out the gate. And our easiest strong acid to describe is hydronium, because it is a very strong acid. It's functionally, when we say hydronium, remember, functionally free protons. They're just supported by a water molecule. Also, please remember when we use these brackets, I'm going to do it for the free proton or for the hydronium. That is the concentration in molarity. That's moles per liter. So if I use those brackets, it inherently means moles per liter of the species in brackets. Examples of strong acids that you should remember: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Now, sulfuric acid has got 2 acidic protons. Only the first loss of proton is a strong acid. The second one is a weak acid, but it is a strong acid for its first hydrogen. Weak acids. Weak acids are pretty much everything that's not a strong acid. That's the easiest way to recognize it. If you memorize your strong acids, your 6 strong acids in the context of this class, there are exceptions. When we go into more advanced chemistry, there are lots of very, very, very strong acids and very, very, very strong bases that bend our rules that we teach in general chemistry. But for general chemistry purposes, and for just laying the really reasonable foundation of chemistry knowledge, if you go back and you remember that these are your 6 strong acids, you're good, because everything else is not in the context of this class. That's my best advice. So whether it's hydrofluoric acid, now hydrofluoric acid, because something's a weak acid does not mean it's not astonishingly dangerous. Hydrofluoric acid will burn the daylights out of you and significantly damage the structure of your bones by replacing calcium in your bone matrix with fluorine. So it's pretty awful stuff. Weak acid does not mean safe. It means that it does not fully dissociate in aqueous solution. That's the true definition. So there's a little bit of a misnomer to that. There's plenty of weak acids which are terrifyingly dangerous to handle. So keep that in mind when you're in lab and you're like, this is a weak acid. But is it a weak acid by definition, or is it a weak acid because it's mild in its action as an acid? So examples of weak acids, and there's too many. I'm not going to hold you to this. However, there are a couple that really pop up frequently. Hydrofluoric acid is a common one. Acetic acid, also quite common. Formic acid, commonly used in our mobile phases in chemistry labs. Carbonic acid, phosphoric acid, also quite common. So these are names you should be comfortable with. You're going to see them a lot, but I'm not going to make you memorize an exhaustive list of weak acids. That'd be ridiculous. So, strengths of acids and bases. How do we get into strength of acid and bases? How strong an acid is really depends on the degree of attraction of the acid's anion to its acidic proton. So the more strongly the anion is attracted to that proton, the less likely it is to give it up. The happier it is to have it bound, the harder it is to let go of it so that it can behave as an acidic proton. So that's really the rationale underlying for what makes something a strong acid. A strong acid needs to readily give up that proton, meaning the attraction between the anion and the proton can't be very strong. It doesn't mean it can't behave as an acid, it just won't behave as a very strong acid. And how do you describe this numerically? Well, we can do this for every weak acid and weak base by just looking at the equilibrium constant of the dissociation of the proton from its conjugate, in the proton in its acid form to its conjugate base. So for this first example, the acid, we have HA being our weak acid compound in water is going to be in equilibrium, forming the conjugate base A minus plus hydronium cation. And the more this reaction shifts towards products, the stronger the acid. We can also say the larger the K is, because of our K being describing, remember from last chapter, our ratio of products to reactants. It's going to favor products, which means the acid reacted favorably. So small ionization constants, K, for these reactions describe weaker acids bases. Large ionization constants describe stronger acids or bases for the reactions as drawn, of course. So this is what I was discussing with that attraction. For the case of strong acids that have complete ionization, like say hydrobromic acid, this hydrogen isn't held on very strongly because bromine, remember, really, really wants an extra single electron so that it can get noble gas structure. So instead of sharing its electron with hydrogen, it's real happy just taking both of those electrons away from that bond and having a sweet octet despite having a negative charge, despite leaving a free proton, which would then react with water forming hydronium. It's very content to do this. It therefore does not have a really strong attraction to the proton. It gives it up very easily, which is why it ionizes completely. Conversely, weak acids, which would be, let's say, any generic capital R, let me redraw that, is just a generic placeholder for whatever structure you're not interested in. Now here we have a carboxylic acid, a COOH, and this is a weak acid. And let me draw in this as an extra bond for clarity's sake. If we have some discussion around this, this is fairly strong bond. It doesn't want to just get rid of this proton. However, if you have some base that's a strong enough base with a nice lone pair, it might be like, hey, I'm more stable having this proton than you are having this proton. So I'm going to take your proton and I'm going to push those electrons onto you. And what this does is puts an extra lone pair on this oxygen, but the oxygen's electronegative. So it's okay with that. But what makes it really okay is that it can share the electrons as a double bond, pushing those electrons up here and make a resonance form, putting electrical charge up top. So it distributes this charge over two positions. And so it can accommodate, it can behave as an acid. It's a decent acid, but it's not a strong acid because it has a stronger attraction to this proton, because this oxygen isn't as electronegative as the bromine, not even remotely. But because we can distribute it structurally across its organic structure, it behaves as an acid regardless, just not a strong acid. So let's move on. And once again, this is rationale. You notice no one's pushing electrons in the book. That's because it's not something I'm expecting you to do. However, I've always learned chemistry a little better when I got more rationale necessarily than I was being expected to recite. But man, if you can make sense of this, it certainly helps. So, moving on. Let's see, acid ionization constants. So, we're talking about dissociation constants just now. We're all comfortable with K at this point. So, let's add a special term for K, for acidic ionization, and we're going to call it Ka, or our acid ionization equilibrium constant. And this term specifically will assess an acid's strength by measuring the equilibrium constant when this acid reacts with water, specifically. So for any generic acid, HA, in aqueous solution, it reacts with water to form an equilibrium where we have hydronium, or you can also say, we'll get here, hydronium plus the conjugate base A minus. Conversely, this can be drawn without water, and we can just look at the dissociation because aqueous implies that it's in water, so this is perfectly legitimate. Generic acid HA dissociates under equilibrium conditions to form free protons plus our conjugate base. Either of these is perfectly acceptable. Technically, the top one's a little bit more correct, but nobody's not going to know what you're talking about if you do the second one, as long as you're aware that free protons always react with water to form hydronium, which is just really two different reactions being housed together in the top reaction simultaneously. So this all said, the equilibrium constant for this reaction is called the acid ionization constant, K sub A, or Ka. That's how I usually say it. And just like a large K means products are favored in any equilibrium condition, a large Ka means we have a situation in which our products are favored, meaning that proton behaved in an acidic fashion. So the big Ka means stronger acid. Whether you view it from the first situation or the second situation, they're equivalent. Regardless, once again, large Ka means stronger acid, or stronger weak acid, or stronger acid. So, I'm not going to make you memorize a whole bunch of Kas. And we haven't gotten to pKa yet, because we have to cover pH and pOH first before doing pKa. But pKa is just a logarithmic transformation of the Ka to make it a more digestible or applicable number. That's what we're looking at here. But I'm not going to make you memorize all these. What I do want you to know is that larger Kas are stronger acids. And you should generally know which acids are stronger than others for the common ones. So acetic acid is one of my favorites, and it has a pKa of 4.74, which, well, sorry, you guys don't have a reference for that yet. But it is acetic acid is the active acid in vinegar. So that gives you guys a bit of an internal reference for how acidic it is. And we have a number of acids that are slightly stronger than it, like benzoic acid, formic acid. And then we get into substantially stronger acids like hydrofluoric acid and nitrous acid and chlorous acid. And all of these are still weak acids, but they're progressively getting stronger and stronger and stronger. So as you do a bunch of homework problems, you'll start to develop intuitions for the relative acidity and basicity of these different compounds and functional groups. Don't spend a lot of energy memorizing all of these right now. Please spend your energy problem solving in the homework and with extra problems and getting proficient at providing solutions to questions. And if you find that you have a gap in those questions that requires some specific memorization, augment your problem solving with some memorization. But memorizing first is not the most efficient way to go about processing all of this material. So now we've talked about ionization. Let's talk a little bit about the interesting property of water with its autoionization, and how it can act as both an acid and as a base in its liquid form. So remember, water is amphoteric, or we also call amphiprotic. You'll hear that used I typically use the term amphiprotic because of its ability to interchangeably hold or release protons. And that is practically functionally interchangeable, with amphoteric being can act as an acid or base. Some books prefer one term over the other. Some use both interchangeably. I kind of came up in an environment where the term amphiprotic was used preferably. because we were very focused on the actual proton transfer. And so, excuse me if I use the word amphiprotic in replacement of amphoteric, even though the text says amphoteric. It's really semantics. So just know I'm not. I am capable of reading, but when I'm just discussing something, if I say amphiprotic, it means amphoteric functionally, and you are allowed to as well. I would never ding anybody for saying amphiprotic in replacement of amphoteric, unless the question was specifically what's the difference between these two, and that would not be a question for this class. So let's take a look at this. So when water acts with itself as an acid and a base to form ions, this process is called autoionization. So what's this look like? Well, inherently, I'm going to draw a linearized water. Remember, this is bent technically. So water, as I've drawn it previously, is bent with two lone pairs, and electrically it's tetrahedral with some compression, so this angle between the two hydrogens is less than 109.5 degrees because those lone pairs take up a little bit of space and they press downward on those bonds. But for clarity's sake, I'm just going to draw it linearized like up here. And these electrons that bind the hydrogen and the oxygen, either set because they're identical, but I'll just do this one arbitrarily. Those electrons can go over here, just spontaneously, and that's going to form your free proton, which can then form hydronium and hydroxide. So every equivalent of water has a unit of acid and a unit of base inherently in it. So if we're looking at a reaction in which an acid, in this case hydrochloric acid, encounters water, it's substantially more acidic than the acidity of the water. Therefore, it's going to give up this proton to water, forming hydronium, and give us chloride. So in this case, the water is going to act like a base. In the case of encountering a base, the water is substantially more acidic than this base, and it's going to give one of its protons to the base, forming ammonium and hydroxide. So in this case, we've got acid, and acid, base, and base. Now, water can act as both acid and base simultaneously, reacting with itself. And what I drew up here with it spontaneously dissociating is essentially what we're seeing here with water and water in equilibrium will form both hydronium and acid. So this is the hydronium definition of what I drew up above, where we said water in liquid form can be in equilibrium forming acid plus base, or protons plus hydroxides. And I should have a liquid next to that water. Sorry for excluding that. Just got a little tight for space. So both the one I drew and the one below are correct. Now, because of this dissociation, the concentrations of acid and base, or hydronium and hydroxide, are equal in water. And this got messed up there. O and H got separated. That should just be OH minus, are equal in water. And the concentration of both of them under normal conditions, 25 degrees Celsius, is the same. And that happens to be 10 to the minus 7 moles per liter. So not a very high concentration, which we know, right? Because they're normal dissociation. But at any time, a normal glass of water at 25 degrees Celsius is going to have a concentration of both acid and base, or hydronium and hydroxide, present at 10.-7 moles per liter. So this gives us a little bit of explanatory power. that we're going to lean on in a couple of different ways through the rest of this chapter and the following chapter. So the product of these concentrations is always the same number, because if they're in equal concentrations under normal conditions, they're always going to be the same value. And this new value is going to be called the ion product of water, or Kw. And this is also known as the dissociation constant of water. And that's how I've referred to it typically. So if we were to just multiply these together as a product, because the liquid water on the reactant side gets excluded in equilibrium, remember, because liquid falls out of any equilibrium concentration determination. So only our products, which are in aqueous form, get recognized in the equilibrium expression. So K sub W is just our hydronium times our hydroxide, and this is 1.00 times 10 to the minus 14th. So this is a very important constant for you to remember. So if you perturb the system by adding acid or base to something else, the normal dissociation of water will stay the same and will shift due to Le Chatelier's principle. Meaning, if you measure any one concentration of either of these two, you can always just calculate the other using Kw as a constant. Pretty slick. In other words, if you increase the amount of hydronium or free protons in solution, the hydroxide has to decrease to keep Kw the same. And conversely, the same is true. If you push up the amount of free base or hydroxide in solution, the amount of free protons or hydronium in solution has to decrease. All the said, acids and basic, acidic and basic solutions. Because of this autoionization, all acidic solutions, or excuse me, all aqueous solutions inherently contain both hydronium and hydroxide ions. So neutral solutions include equal amounts of hydroxide and hydronium, or free protons and hydroxide. And at that level, we see both of them equal 1.00 times 10 to the minus 7 moles per liter for their concentrations. Any solution that's acidic have to have higher concentrations of free protons / hydronium. This means that the amount of hydroxide has to decrease to maintain Kw. So in these cases, any acidic solution is going to have a concentration of hydronium or free protons which is greater than 1 times 10 to the minus 7th, and under those circumstances, free hydroxide is also lower than 1.00 times 10 to the minus 7 moles per liter. And the exact opposite is true for basic solutions. So now we're going to get into measurement, because we've been doing some descriptions of how strong an acid is, how weak an acid is, and looking at relationships of how acids and bases behave. But we have to get to the nitty-gritty of how we measure acidity. And the way we do this is through pH, which thankfully we're all relatively comfortable with. I dragged my cursor around here. Let me fix that. There we go. So this is the most common way we really evaluate acidity or basicity. And all pHs, and I'm going to draw it my way because I like free protons, is pH equals the negative log of the concentration of protons in solution. And the book calls it the same thing. It's the negative log of the concentration of hydronium in solution. And that's fine. So the pH of basic water, excuse me, not basic, of normal water, where it's just autoionizing, is the negative log of 10 to the minus 7 moles per liter of hydronium. And when you solve for the negative log of 10 to the minus 7, that equals 7. So the pH of normal water is 7. So all you need to do to know what the pH is is find the concentration of free protons / hydronium. Conversely, if you ever need to know what the concentration of hydronium is, all you need is the pH. Now, here's the important part. Low pH is acidic. High pH is basic. 7 is neutral. So if it's lower than 7, it's acidic. If it's higher than 7, it's basic. If it's 7, it's neutral. A couple tips. The second to last bullet here is just a solution for pH. So if you want to solve, if you have pH and you want to know what the concentration of protons are in solution, if you have pH equals negative log the concentration of protons, and you want to solve for the concentration of protons, you need to raise both sides to the 10th, to an exponent. So we'll multiply both sides by -1 and raise both sides by 10 to get rid of the logarithm, and that's what you're looking at here, where the concentration of protons is equal to 10 to the minus pH. Likewise, because of what we know from the constant Kw, the concentration of hydroxide and the concentration of free protons in solution, or hydronium in solution, is equal to 10 to the minus 14th power. Let me scoot ahead here and see what we're looking at in terms. Okay, we're almost there. I know you guys are a little bit. Oop, here we go. I'd be a little overloaded too right now, but we only have a few more slides, 3 more slides, and we're through this hour lecture. So, and then we only have 1 more to go, and we are through chapter 17 plus a recitation. So, this is crazy. I don't know why I'm losing my continuity here. So what does pH imply? I think we may have already talked about this in a little bit, but remember, lower pH below 7 is acidic. The lower it is, the more acidic it is, and the higher it is, the more basic it is. And because this is a log-based system, for every unit pH, it's a factor of 10 difference in acidity, just like an earthquake, right? An earthquake of 6 shakes you, so hard. An earthquake of 7 shakes you 10 times harder. So everything here is a log-based scale. So a unit of change is actually a pretty substantial change. And our normal range that we deal with is 0 to 14, with 0 being our most acidic and 14 being our most basic. And that's based on the acidity of protons and the basicity of hydroxide. There are plenty of things that are vastly more acidic and more basic than those. However, for the context of this class, we're going to go 0 to 14. Don't worry about those. And another thing is, if you're calculating significant additions associated with any of these, particularly in a laboratory setting, remember that only decimal places are significant in pH values. The first one doesn't matter. So just like we have pH, we can also have POH. And the only thing about this is it's another way of looking at it. So POH is just the negative log of the concentration of hydroxides. That's it. Everything else is functionally the same. It's the exact opposite of pH in every way. And what's cool about this is, if you have pH and somebody wants you to know what the POH is, or calculate that, you just go to this relationship. Because for any solution, pH plus POH is going to be 14. Pretty straightforward, right? So if you know pH, you inherently know POH and vice versa. And so we're going to ask you to do some calculations around this, but don't get hung up on it. This is not, don't let this one confuse you. And that's really what this whole last slide is looking at. It's just confirming pH plus POH at 25 degrees Celsius, which is standard conditions, is 14.00. So anytime you know one, you are just a hair's breadth away from knowing the other. No problem. And then if you, let's say, know the pH and you're asked what the concentration of hydroxide is, you would calculate POH, and then you would just use the equation for POH to solve for the concentration of hydroxide ions. So not Nothing too wild there. And that is it for today. So I'm going to get this one posted up, and then in the next day or two, we'll jump in and we'll do part 2 of the chapter and get you guys through the rest of chapter 17. All right, have a good day.